Hi folks, in this question we are going to review how to sketch functions as transformations of simpler functions. So if you take a look at the function we have here, you can see that it's related to a simpler function that we know. It's related to the function y equals x cubed, all right? Because we have a variable and it's being cubed. And the reason why we can treat it as a transformation is all the operations that are happening to the variable are additions, multiplications, divisions, subtractions. So here it's being multiplied by 2, multiplied by subtracting by 4. That's what's happening to the input. And then after we cube it, so in other words, after you take the cube, which is the function we're working with, we see that the y value is then multiplied by -1/2 and -1. All right. So this function y, again, can be seen as a transformation of this function f. So what is this? The set of transformations? So we're multiplying the y values by -1/2. Okay. And of course, f represents the y values. And then, of course, we're going to be subtracting those y values by 1 later on. Okay. Let's look at the input here. We have to be careful because in order to correctly identify the transformations, the horizontal transformations, the input needs to be in factored form. So while this might look like horizontal stretch of a factor of 1/2, because we also remember that horizontal transformations always have the opposite effect. So instead of multiplying by 2, we're dividing by 2. And then moving to the right, so -4 instead of left, this says to the right, we have to have it in factored form, which tells us that it's in fact moving to the right by 2 units. Okay, so this is another way of representing this function as a transformation of this function f at x, which in this case here happens to be x cubed. All right, so the reason why it's nice to write it in this form is that this demonstrates that transformations work the exact same way regardless of what your parent or original function is equal to. Okay, and this gives us the recipe for what we do to a point on x cubed to transform it to a point on this function y. Okay, now one of the nicest ways to show this is to actually transform some points explicitly. It's going to make graphing it later on much simpler. Okay, now one thing to keep in mind, and I'll draw it down here, is we know what the function y equals x cubed looks like. The original function looks like this. Okay, and the one thing that transformations don't do is change the general shape of the function. So what you want to do is you want to pick some points, okay, that are going to help you, once you transform them, graph this other function. So the obvious one to take, well, would be this point at 0, 0, because that's where it sort of switches from, has that little squiggle going on. And then you could take 2 points on this side, 2 points on that side, but what I'm going to suggest is always take a point on either side of some really important point. So what I'm going to do is I'm going to take a point here, which is going to be 1, 1, and then I'm going to take this point on the other side, -1, -1. And these are the 3 points that I'm going to transform, and I know that this shape, that cubic shape, will be kept. Okay, so you can show this in lots of ways. Okay, I'll show it this way here. I'm going to start with my points on my parent function. And now I'm going to transform them. Okay, so I'm going to take the x values, and let's remember what these transformations do to the x component of my point. Okay, all the horizontal transformations have the opposite of effect. So what does this 2 do to the x value? Instead of multiplying by 2, we divide by 2. Instead of subtracting 2, we add 2. Okay, and that's now going to give us the x component of that first point. And in fact, I can just do all the x components. So here, what's it going to do? It's going to take this 1 divided by 2 and then add 2. It's going to take this -1 divided by 2 and then add 2. And then we can now do the y values, and these are the same effect Okay, meaning here I'm going to be multiplying by negative a half and subtracting 1. So I'm going to take this 0, I'm going to multiply it by negative a half. Okay, of course I know that's going to be 0, but I just want to show very explicitly what I'm doing. And then here, subtract 1. Okay, and that's going to be my point. Here I'm going to take negative a half multiplied by 1 and then subtract 1. And then lastly here, negative a half times negative 1, the y value, and then minus 1. Okay, and now finally I'll have the points. Okay, so here what are we left with? Well, 0 plus 2, so we're left with 2, and here we're 0 minus 1. So this point here, which is going to be between the other 2 points, is now being transformed to negative 1. Okay, what happens with this one here? So a half plus 2. So since I have to put this on a graph, I'm just going to put it in decimal form. And then you have here, so negative 0.5 minus 1 is negative 1.5. And then lastly here, you have negative a half, so negative 0.5 plus 2. This is going to be 1.5, okay? And then here we have 1 half, so 0.5 minus 1 is negative 0.5. All right? And so now that I've got these 3 points, I can now draw myself a fairly decent graph. I notice these numbers are not particularly big, so I might even go up by 2 instead of make each box 1. Okay, and I notice here that when I look at my x values, they're all on the positive side. So I'm going to put my y-axis further to the left to not waste too much space on my graph. And then here, I notice all the y values are negative. So similarly, I'm going to put maybe I'll put it up here so that I don't waste too much space on the graph. Okay. And here I have to go to 2.5, so 1, 2, 2.5. So I think that's what I'm going to do. I'm going to go up by, so this will be 1, 2, 3, 4. So this will be 2. Okay. And then here, this will be negative 1, and this will be negative 2. Okay, just give myself a lot of room on the graph. Okay, you don't have to be going up by the same amount on x and y, but we had enough room to do so. Okay, so 2, negative 1. So we know that this is going to be our center point. Then our 1, 1 becomes 2.5, negative 1.5. So 2.5, negative 1.5. There we go. And then this point, negative 1, 1, becomes 1.5 and negative 0.5. Okay, now this is where you have to be careful because this looks like a straight line, but of course we know it's not a straight line. It's going to have to keep the same shape as my original cubic. Okay, so you just kind of, what I'd suggest is kind of just trace it out first before you commit to drawing it, and that looks pretty good. So now I'm going to commit to drawing my graph. There you go. And there is my transformed function, okay, looking at it as a transformation of y equals x cubed. All right, so let's recap. Number 1, the input, number 1 actually is to identify what your parent function is. In this case here, it was pretty clearly x cubed. Number 2 is to make sure the input is always in factored form. And then number 3, pick 3 points, key points on your graph of the original function to transform the points, and then before you actually draw the function, make sure you're choosing a good location for the x and y axes and choose a good scale depending on how much room you have. Okay, that's it for this one.